Hi everyone. In this video, we will discuss convergence tests for series, looking at several examples with particular emphasis on the proofs of these convergence tests. To begin, you may recall from a Calculus 2 course that there are many convergence tests for series. So in a Calculus 2 course, you may have seen the comparison test, the limit comparison test, the integral test, ratio test, root test, alternating series test, a test for divergence, or an nth term test. There are many named convergence tests for series. Now, you may have seen most of these, but perhaps not all. In fact, in my own background, I never saw root test until I actually was later on for the first time teaching a Calculus 2 course. Um, but nevertheless, these are a fairly standard list of the tests that are usually covered in a Calculus 2 course. Um, Now, you might wonder sort of why are these the tests that we teach? And there are a couple of possible answers to that. It could be that these are the tests, right? These are just all of the tests, and so we teach all of them. But it actually turns out that that's not the case because there are many more convergence tests, right? So here is just a partial list of other well-known convergence tests. As you can see, at some point, many of these are just named after the mathematicians who first proved these results. But going back to this first list, uh, there really are sort of a couple of answers to why we tend to teach these tests. The first is these cover a lot of the fairly standard examples you would want to understand, right? So these allow you to deal with both with series that contain positive terms and positive and negative terms. So, for example, you have alternating series tests in here. The standard statements of ratio and root test allow you to deal with positive and negative terms. So you have some things there. Comparison, limit comparison, and integral test give you nice ways of comparing unknown series or series whose convergence you don't yet know about to fairly standard P series, geometric series, things that you do already know the convergence of. So on the one hand, like this list of tests here, they're all fairly basic. They're all fairly straightforward to apply, and they work on a wide variety of series that one might encounter. But of course, they don't cover every possible case. So, for example, and we'll talk a little bit more about this in a bit, but like the ratio test, there are cases in which the ratio test fails to determine convergence or divergence. So, what happens in that case? Well, if you actually start here, the sort of second half of this list, these are really all just adding on to the ratio test and dealing with what happens when the ratio test fails. So each of these, this is not exactly maybe a hierarchy, but sort of a hierarchy of things you might try once the ratio test fails. You might try Rob's test and Bertrand's test and Gauss's test, so on and so on. So many of these other tests take that sort of base layer of tests and then sort of try to fill in the gaps, right? So when you have a series for which one of the tests on this list does not work, then maybe one of the tests on this list will work. And of course, there are even more convergence tests that aren't listed here when you start looking at particular types of series. So for example, if you study Fourier series, there are particular convergence tests. There's one called Dini's test to help you determine whether a given Fourier series converges. So again, there are many more outside of this. So all of that being said, what we are not going to do is to try and state and prove every possible convergence test, nor will we try to look at examples, for every one of these series. Not that that is not a valuable thing to do. In fact, I would encourage you to go and do some poking around to learn about some of these. On the homework, I'm actually going to present to you a new convergence test you've never seen before and let you work through the process of trying to apply it. Because the valuable skill is not necessarily to have all of these memorized, it's to be able to apply them when you need to determine whether or not a given series converges. So what our goal will be for this video is to look at just a few examples of convergence tests. They're all going to be convergence tests from that first list. So we'll look at comparison test, the ratio test, and the root test, and then to use those as sort of examples to work through, and we'll work through the proofs of those to understand how they work. I've selected those because each of them has sort of certain characteristics within the proof itself that we will see if we were to go and sort of maybe even look at some of these other tests, right? So they're sort of nice prototype proofs, which really show you how you might prove other types of convergence results as well. So let's first look at the comparison test. So let some of the ANs and some of the BNs be series. So this first condition is saying that each of your terms of your series, so all the ANs and BNs are strictly positive, and we're going to assume that the terms of your series AN are less than or equal to the terms of your series BN. Now, we're going to assume this holds eventually, which is to say that we're going to assume that this holds for all little n beyond some capital N, right? So we don't need this to hold for every term. We just need it eventually to hold, okay? And so this says if this inequality holds eventually, then if the sum of the BNs converges, then the sum of the ANs converges. So if said another way, if the larger series converges, then the smaller series must converge. And the second part says if the smaller series diverges, then the larger series must also diverge. Now, it can be helpful both in eventually proving this and also in just thinking about this to consider a visual. So imagine that you have two balloons. The balloons are identical in makeup, in material, in all of these factors, okay? And we are going to think of the smaller inside balloon as being sort of the sum of the ANs and the larger balloon as being the sum of the BNs, or I guess AKs and BKs. So the idea here is that the sum of the AKs, that's sort of each AK is a little puff of air that you're putting in the balloon. And the BK, each BK is a little puff of air that you're putting in the balloon. And what you know is that each of those puffs, the puff that you're putting into A is always less than or equal to in volume than the puff that you're putting in the BK, right? So this light orange balloon is always, every time, getting either the same amount of air as the dark orange balloon or a little bit more, okay? And so what the comparison test really says is, you start here, and if eventually the puffs that you're putting in the dark orange balloon are less than or equal to the puffs that you're putting in the light orange balloon, then as these blow up, well, if the bigger balloon doesn't pop here, right, the one that you put more air in, if it doesn't pop, then guess what? The smaller balloon also doesn't pop. And here we're thinking of doesn't pop as converges, right? So if this larger series converges, then the smaller series must also converge. On the other hand, same setup, we're always putting smaller puffs of air into the dark orange balloon. Then as we blow it up, if this dark orange balloon on the inside over here, if it pops, well, then if they're identical in makeup, this other balloon will be larger. It must also pop, right? Now, we replace pop here with the notion of diverges, right? So if the dark orange balloon, or sorry, if the sum of the AKs diverges, then the sum of the BKs must also diverge. Now, this is a helpful way. It'll actually be sort of a slightly helpful in thinking about how we're going to prove this. So we're really thinking about what happens each time as we increment, and we're incrementing slightly more for one than the other. But this is also helpful if you're ever teaching this as sort of an analogy to help students remember, what actually happens if the larger series converges, the smaller one converges. If the smaller one diverges, then the larger one diverges. This is something that students often, if they don't build some sort of mental model for how this is working, it's very hard to remember sort of what happens, and they'll mistakenly say things like, "Oh, well, the AKs are always less than or equal to the BKs, and the sum of the AKs converges, so the sum of the BKs converges," right? They just get these implications backwards. And so this is a helpful mental model for them to have to both understand a little more deeply what's going on and have a more intuitive sense of why this works, but also just to simply remember the test correctly. So now we actually want to be able to prove the comparison test. And so we want to be able to prove each part, right? So the first part, we will recall, is simply that if the larger sum converges, then the smaller sum must also converge. Okay. So for part one, okay. So the first thing I'm going to do is I'm going to set up some notation. So I'm going to let capital A sub n just be the sum k equals 1 up to n of the AKs. I want B sub n to be the sum k equals 1 up to n of B sub k. And since we know, so the capital A sub n, this is just going to give us the sequence of partial sums for the series AK. The capital B sub n is just going to give us the sequence of partial sums for the sum BK. And I'm going to set, in this case, remember in this case, we know that the larger series converges, so I'm going to set this to be whatever that value of the sum converges to. Okay. All right. So the first thing to note, one of my assumptions is that at least eventually, okay, all of these terms are positive. Okay. So what I might want to do is I might want to sort of break off the parts where the series actually satisfies that criteria. Okay. So since 0 is less than AK is less than or equal to BK, eventually, I want to choose a capital N such that this holds for all K greater than that capital N. Okay, so then a couple of things. Then if I look at these, now that I know this is true, that tells me what? That tells me each of the things I'm adding on each time is now, I know, positive, right? So then AN and BN are both monotone, increasing. Here. Okay. And so if I look at So note that AN, well, whatever AN is, it's each of these terms is eventually going to be less than or equal to the terms here. So what I'm going to do is I'm going to say AN is, well, first just equal to. So I'm going to first write AN is just equal to the sum K equals 1 to N of AK. And I can write this. So what I'm going to do is break this up. I'm going to go up to capital N. Okay. Now here I'm assuming this can really only work when little n is greater than capital N, and that's fine. Okay. And now what do I know? Well, I know that this will be less than or equal to. So I'm going to leave this first part alone. So let's begin our proof of the convergence theorem. We'll start with the first case. Okay, so remember this first case is essentially that if the uh, if the larger series converges, then the smaller series must also converge. Okay. Um, Now we have this condition that inequality, 0 is less than AN is less than or equal to BN. We have that needs to hold eventually. Now, what we actually want to do, for any infinite sum, any finite chunk of terms at the beginning sort of doesn't really matter because it's just a finite sum, right? It's the infinite bit at the end that really matters. So what we're going to do is we're going to assume without loss of generality, okay? So without loss of generality, we're just going to go ahead and assume that 0 is less than AN is less than or equal to BN for all natural numbers n. Okay, so just assume that this condition holds for every term. If it doesn't hold for every term, then you just have to do a little more bookkeeping. You have to break off this finite sum, or the finite chunk of terms at the beginning where this doesn't hold, and then you apply everything to the sort of end part. Okay, but it's really not, it doesn't change the essence of the proof in any significant way. Okay, so since these are, or sorry, so since A sub n is less than or equal to B sub n, we note that if I take any finite number of terms, right? So since the A terms are always less than or equal to the B terms. If I add up the first n A terms, then that has to be less than or equal to the first n B terms, right? Because each of the individual terms is less than or equal to. But notice that, so setting AN to just be this, so this thing on the left, right, this is really the nth term in the sequence of partial sums, right? So this is my sequence of partial sums for A. And similarly, I could do the same thing for B. So we have, this is just saying that AN is less than or equal to BN, right? And BN, by assumption, right? Our assumption is that the infinite series of the BKs converges. So that tells me that BN is converging to something, let's call it B. Hence, if I look at my ANs, right, it must be less than or equal to B. Each of these is increasing, right? As I add on more terms, this is increasing because each of these terms is strictly greater than 0. So whatever this is doing, this is increasing, and it's increasing and converging to B. So each AN is bounded above by each BN, but each BN is less than or equal to B. So AN is less than or equal to B. But now what do we have? So if I look at AN, it's bounded above by B, and it's also monotone increasing. Now, why is it monotone increasing? Well, every time I add on one more term, that term is positive. So my partial sums are getting larger every time because I keep adding on these positive terms. So AN is bounded and monotone, and by the monotone convergence theorem, I'm going to abbreviate the monotone convergence theorem, MCT, AN converges. Okay. So the idea here for the comparison test is when you have a sequence of positive terms, sorry, a series of positive terms, then the sequence of partial sums that results from that series is a monotone sequence. So here I'm able to get convergence just by showing it must be bounded above by something. The thing it has to be bounded above by is the thing that the series BK is converging to. Okay, so in a way, back to that balloon analogy, what you're saying is, well, this red balloon is blowing up, it's getting bigger and bigger and bigger, but it's caught inside of this B balloon, right? Then I know as I keep adding in these puffs of air, it never pops. Okay, so A can't pop either. It must settle down to some size, which is what it converges to. Okay, so in this case, right, we see that we get via the monotone convergence theorem convergence of this series. So again, we identify infinite series with their sequences of partial sums, and then we can just use the sequence of partial sums to prove different types of theorems. Now, in this case, we have this condition that each of my terms needs to be positive, and that's a very helpful theorem or a very helpful hypothesis because it tells me things about my sequence of partial sums. For example, it tells me that my sequence of partial sums must be monotone. Okay. Now, in the second part of this, we're going to get some more help from the fact that this sequence of partial sums, that each of the terms in this series is positive. That's going to give us a sequence of partial sums that is monotone And what we'll see is there, the monotonicity is going to give us some help, but in a slightly different way. All right. So improving the second part, and I'm going to reuse some of the same notation. I'm going to use the same assumption that this inequality holds for all of the terms. But then let's see what happens. So in that case, we're assuming that the smaller series diverges, which means the sequence of partial sums diverges. So if AN diverges, now let's think about this. AN is monotone, right? AN is still monotone because we're just adding on positive terms every time. So the little a sub n's, the terms in the sequence, in the series, are getting added in to give us our next term in our sequence of partial sums. So our sequence of partial sums is monotone, but it diverges. Well, there's really only one way that a monotone sequence, a monotone increasing sequence, can diverge, and that's just to run off to infinity. So if AN diverges, since AN is monotone, AN must, essentially it must be unbounded. And in this case, it's increasing, so we know it's unbounded above. It's running off to infinity. All right. Now, how can we help this, or how can we use this to help us say something about the series of BKs? Okay. Well, what does it mean for AN to go off to infinity? Then for each natural number K, there exists another natural number. And now this natural number is going to depend on our K, so I'm going to call it capital N sub K. Such that what? Well, basically, the terms in my sequence of partial sums must get greater than each K eventually. So the A sub N will be greater than K for all little n greater than capital N sub K. So basically what this is saying is if your sequence goes off to infinity, what that really means, the definition is, for any natural number, I can go far enough out in my sequence such that I'm eventually above my A sub n's are eventually always above that natural number. And I can do this for each natural number, okay? But what do we know? We know that the capital B sub n's are always greater than or equal to the A sub n's, okay? Well, so what does that tell me then? That means that for each K, there exists a natural number, capital N sub K, such that B sub n is greater than K for all little n greater than nk. Okay, and hence, this means that the B sub n's also diverge to infinity. Okay, so since AN diverges, it must diverge to infinity. We just write out what it means for A sub n to diverge to infinity. We use the fact that the B sub n's are always greater than or equal to the A sub n's, and hence this by definition actually just straight up tells us that the BN's diverge to infinity. Okay. So in this case, we're again using the monotonicity. So this fact that we have positive terms in our series gives us a monotone sequence of partial sums, and the fact that that sequence of partial sums is monotone is very powerful. It allows us, in some cases, to use the monotone convergence theorem, or to just use facts like the only way a monotone increasing sequence can diverge is to be unbounded, is to run off to infinity. Okay. So again, these are all very powerful results to be able to use. Now, once you have the comparison test, there's also the limit comparison test, which is a generalization of the comparison test, and it's just helpful in maybe eliminating some. I guess the best way to say it is you trade off some of the algebra that a comparison test might require often for just a limit calculation. And of course, there are things that the limit comparison test does a little bit better also otherwise than the comparison test. But it's really just a generalization. The book does have a proof of the limit comparison test if you'd like to take a look at that. Um, but I now want to switch over to the ratio test. Okay, another very standard convergence test that we see in a Calculus 2 course. Now, the version I've stated here is actually slightly different than what you would see in your Calculus 2 course. So we'll talk about this version first, and then in a little bit we'll talk about how this is a bit different. So the version as stated in the book says, let the series A sub n be an infinite series of positive terms. So I'm assuming that all of my terms here are positive. And set, if this limit exists, R to be the limit as n goes to infinity of this ratio. So this is just the ratio of successive terms, right? So this is the n plus first term divided by the nth term in your series. So the ratio test says if this value R is strictly less than 1, then the series converges. Skipping over here to 3 for a second, it says if the value R is strictly greater than 1, then the series diverges. However, if R is equal to 1, then the test fails. And that is to say that the series could converge or diverge, that we can't say for sure which happens if R is equal to 1. But if R is strictly greater than 1 or R is strictly less than 1, then we can determine whether the series converges or diverges. Now, just looking at this, you may sort of, if you look at these conditions and think, okay, I have a series that converges when R is less than 1, diverges when R is greater than 1. This looks like a result that we've seen before, which was the result for geometric series, right? So we know that a geometric series will converge if, so generally we'll write a geometric series as a sum A R to the K equals, say, 0 to infinity. And we know that this series converges if R is less than 1 and diverges if R is greater than or equal to 1. Now, this looks very similar, right? So this looks like I get convergence when R is strictly less than 1. The equals 1 is where it differs, right? Here I know, and sorry, these should be absolute values, actually. But if we're dealing with positive terms, our R values are only ever going to be positive. So the equals 1 case is really where it differs, because here this says for sure diverges, here this says fails. Here this says diverges, though, and that matches up with this. So it looks similar to what we get for geometric sequences. And in a lot of ways, right, if you look at, so take this geometric sequence, what is the ratio? A sub n plus 1 over A sub n. Well, okay, I take the n plus first term here, that would be A R to the n plus 1, divided by the nth term would be A R to the n. A divided by A, assuming A is non-zero, right? Which again, my assumption here is that these are positive terms, so A couldn't be 0 if I was trying to apply the ratio test. So those could be canceled. And then R to the n plus 1 divided by R to the n would just be R. What you see here is that even without taking the limit, this ratio for a geometric series is always R. So you actually recover a lot of the same result. Now, so what is the ratio test doing that's different? The ratio test doesn't just apply to geometric series. And in a lot of ways, what it's trying to do is it's trying to encapsulate the idea that a sequence could be almost geometric in the limit, right? So as we go far enough out, the terms are like almost multiples of each other, right? So it's almost like they have a common ratio. And this R that you're trying to calculate is somehow the approximate ratio of terms in the limit. Okay. So again, what you're trying to do is, in a way, compare this, not compare in the sense of comparison test, but you're trying to draw an analogy between geometric series and other types of series by looking at these ratios. All right. So let's prove the ratio test. Okay. So again, we have three parts. We're going to do most of our work here in the first part. Okay. So in the first part, we're going to assume that R, that limit value, is strictly less than 1. Okay. So suppose R is strictly less than 1. And then what I'm going to do is I'm going to choose a value capital R such that capital R is between little r and 1, right? So since little r is strictly less than 1, right, I can always choose some other number that's strictly between little r and 1. I could write down exactly such a number if I wanted to. For example, if you average little r and 1, that will give you a number that's strictly between these two. But we don't need that exact value, and so we'll just call such a number capital R. All right. Now, since R is little r is the limit as n goes to infinity of a sub n plus 1 over a sub n, well, eventually, right, this ratio must get less than capital R. Why? Well, if it never got less than capital R, little r couldn't possibly be the limit. Okay, so since little r is equal to the limit, let me say this, then a sub, then I made the same mistake again. I need to write a fraction here. And then here we go. A sub n plus 1 over a sub n must be less than r for all n sufficiently large. Say all n greater than some capital N. Okay. So eventually, this ratio has to get less than this capital R, because if it didn't, then it couldn't approach little r in the limit. All right. So if I look at a sub little n plus 1, or sorry, a sub capital N plus 1, this is going to be less than capital R times a sub capital N, right? So that's just multiplying both sides of this by a sub n, right? And again, since that's positive, I don't have to worry about this being 0. Okay. Now, if I look at a sub capital N plus 2, well, let's see. By definition here, this is just like plugging in capital N plus 1 here. Okay, and then multiplying over this would be less than r times a sub capital N plus 1. But a sub capital N plus 1 is less than r times a sub n, so this is less than r squared a sub capital N. Okay, and we can keep doing this, right? So a sub capital N plus 3, if I repeat this same process, backtracking through here, right? So this would be less than r a sub capital N plus 2, but a sub capital N plus 2 is less than r squared a sub n times another r, give me r cubed a sub n. And in general, a sub capital N plus k is going to be less than r to the k times a sub capital N. All right, so now what happens then if I add up so if I look at now the sum, let's say m equals 1 to infinity of a sub m, what's that going to be? That's going to be the sum m equals 1 up to capital N of a sub m plus a sum m equals capital N plus 1 up to infinity of a sub m. Okay. Well, if I look at this, so this is just some finite sum. If I look at this piece, this is really the sum of all of these subsequent terms, right? So it's the sum of a sub capital N plus 1 plus a sub capital N plus 2 plus a sub capital N, so on and so on and so on. So I could express this as the sum. And what I'm going to do here is I'm going to write this as the sum of, for k equals 1 up to infinity of a sub capital N plus k. So really, what I'm doing from here to here is really just a reindexing. And I'm only working on this sort of second sum here now. Now this, if I look at this, this is, and sorry, now I want to make this a less than. Because what I'm going to do is I'm going to replace each of these terms with r sub k a sub n. So I'm using, for each of these terms, I'm using this inequality here. Okay. But now notice that this a sub capital N, that's a constant as far as this sum is concerned. Okay. So what I can actually do, and just to make save a little space here, I can just pull this a sub n out of the sum. So I get plus a sub capital N times the sum. And now if I look at this sum, this is just a geometric series, right? This is the sum k equals 1 to infinity of r to the k. And because I have assumed that capital R is strictly less than 1, this geometric series converges. Okay. In fact, so if I again just leave the first term alone, this will converge to r over 1 minus r. Okay. And so what I have here is that this sum is less than, right, this finite sum, right? Finite sums always converge, plus this term. So this series converges. So this gives me also some finite value. So now I have that this sequence is bounded above by the sum of these two finite values. Okay. Hence, each of these terms was, right, or well, now you have this whole sum, right, which is bounded above by some finite number. It must also be finite. And so this series converges. Okay. Now, I want to skip 2 for a second, and I want to skip to 3 because the proof of 3 is nearly identical. Okay. So in 3, the only difference is going to be, so I'm going to, let me get a color here. So in 3, let me just switch. Let's use orange. Here we go. Okay. Okay. So when I go to proof 3, the difference is I'm going to assume R is greater than 1. But then I'm going to choose a capital R. I'm just going to flip these inequalities around. Okay. So I can still choose a capital R between little r and 1. It's just that now that's bigger than 1. And then this will all work except this inequality will be turned around. Okay. And now all of these inequalities will be turned around. Okay. And now when I come over here, all of this is still the same. This is just equality, and now this inequality is just going to be turned around. Okay. But now what are we going to have? Now we're going to have that this geometric series, still a geometric series, but now R is strictly greater than 1. This will diverge. Okay. And so now you can't write that it's equal to anything, right, in this case. But now since this is going off to infinity and this is even larger, this must also diverge. Okay. So the calculations, the proof is nearly identical in case 3 when R is greater than 1. You just flip all of the inequalities around and follow the natural consequences of that. Yeah. Now, I'm not actually going to write out anything for part 2. And the reason I'm not going to do that is that there's really, if you think about it, you want to prove that the test is inconclusive. Now, what would we need to do? Well, we would need to find 2 series, right? Where when you calculate the value little r, you get 1 for both of them, but one of them converges and the other diverges. There are plenty of examples you could choose here. Perhaps the 2 easiest are to look at the 2p series. So one is the sum 1 over n squared, and the other is the sum 1 over n. So if you look at the sum 1 over n, we looked at that in a previous video, that series diverges. If I calculate r, I'll get that it is 1 in that case. Okay. If I look at the series 1 over n squared, we haven't talked about that one as much, but it actually converges. But if I calculate the r, I also get 1. So what I see is I have 2 series that when I calculate their r, I get 1 for both of them, but one of them converges and the other diverges. Therefore, the test must be inconclusive when r is equal to 1. Now, as I mentioned briefly earlier, there are a lot of refinements to this test. There's sort of the version we've talked about here. I mentioned that you can actually take this, and in fact, the way it's stated in a lot of calculus texts is that we remove this requirement that we have positive terms, and we instead look at these with absolute values. Okay. Now, the problem here is, or not the problem, but what you have to deal with is you actually need another condition to basically ensure that you don't have a whole bunch of zeros, right? Because if you have too many zeros, like this limit can fail to exist because you have a bunch of 0 terms. So there are other conditions that need to be added in to make this work here. But a very common version is to remove this condition that you have positive terms and add in absolute values here, and the results are the same. You can actually say slightly more by replacing this limit condition with some conditions on lim imps and lim sups, which are related to limits but not the same. Of course, when the lim imp is equal to the lim sup, then the limit exists. So you recover the same thing. So there's the original sort of version by D'Alembert is I think uses the lim imps and lim sups. But then again, you have these Rob's test, Gauss's test, Kummer's test, lots of other tests that again try to take on, really a lot of them are taking on what happens here in the R is equal to 1 case and trying to help tease out the behavior there. All right. So the last test we want to look at is the root test. So the root test says let an be an infinite series of positive terms. Again, in some versions, you replace that condition on positive terms and just put absolute values here. But we're going to just prove this version with positive terms. And set if the limit exists. So this is not a p, it's a rho. So set rho equal to the limit as n goes to infinity of the nth root of an. Now, this theorem says, and again, it looks sort of similar, but it's different, obviously, than the ratio test. So if this value rho is less than 1, the series converges. If rho is equal to 1, the test fails. And if rho is greater than 1, then the series diverges. So again, these conditions on rho look the same and the resulting conclusions. However, right, what rho actually is something slightly different. Okay. So let's conclude this video by proving the root test. And the proof of the root test is actually fairly short. And you'll see some similarities to the ratio test. Okay. So in the first case, we're going to suppose rho is less than 1. Okay. And we're going to choose a value, capital R, such that rho is less than R is less than 1. Okay, so exactly same thing we did before, right? Since rho is strictly less than 1, I can choose a value capital R that's between rho and 1. Now, what does this mean? Well, this means eventually, so since rho is the limit, as n goes to infinity of the nth root of a sub n, then the nth root of a sub n must be less than this capital R eventually. Right? If it never got less than that capital R, there's no way its limit could be rho. So eventually this has to hold. Now, I'm going to not write out quite as much of the technical detail as we did before, right? I could say, what does it really mean for this to hold eventually? It means there exists a capital N such that this holds for all little n beyond that capital N. But we can drop a little bit of that formality now. So then if we use a comparison test, so using the comparison test, okay, so capital R is strictly less than 1, so this is a convergent geometric series. And if we look at this, this really says, if I were to rewrite this, this says a sub n is less than R to the n. Okay. So since this converges by the comparison test, this must also converge. So in a lot of ways, a root test is very similar to the ratio test in that you're somehow comparing this to something like a geometric series. Okay. All right. In the third part, you can essentially flip this around, right? So if I wanted to prove this for the third part, so rho is greater than 1, choose R such that this happens. Since rho is equal to this, and eventually my terms must be greater than R, using the comparison test with this, which will now diverge because capital R is greater than 1, we would see that this diverges. Okay. Now, the last thing you need, right, is in the second case, you just want to show that the test fails. Again, there's not a lot to write out here, but I'll just write out. So you can again use the same examples. So if I take the sum of 1 over n's and the sum of 1 over n squared. So here, if I calculate the value rho would be equal to the limit as n goes to infinity of the nth root of 1 over n. If you calculate this, you will get that this is 1, but we know that this series diverges. Okay. So I've got when rho is equal to 1, here's an example of something that diverges. Also, though, if I calculate rho here, this will be the limit as n goes to infinity of the nth root of 1 over n squared. This will also be equal to 1, but this series converges. Okay. And so you have here examples where you get rho is equal to 1 in both cases, but one diverges and the other converges. Therefore, the test must be inconclusive. Okay. So what we've seen are 3 examples of convergence tests. Okay. And what we are seeing is really different ways to use facts and hypotheses about the series in order to prove something about the sequence of partial sums in most cases, right? Now, again, this is just a very small sample of the wide world of convergence tests. I will also post in the course some links to some other lectures that really just review, how to apply some of these series. We won't spend a lot of time, how to apply some of these convergence tests. We won't spend a lot of time applying convergence tests, but I will on a homework have you, use a few of these things just to remind yourselves how they work, and also to have you explore one that is not a part of a standard calculus sequence and also doesn't appear in our book. But what I really want you to take away from this is, again, series are really just sequences of partial sums. So when we go to prove things about the convergence of series, they're really just the same as proving things about the convergence of certain types of sequences. Now, of course, once you build up, we saw in this last example here with the root test, we were able to prove the root test using the comparison test. So really what you have are these specialized sequence convergence results, but I say they're specialized sequence results, but they're just series results that you can then start to apply to other series. But at the end of the day, this all comes home to proving things about convergence of sequences, because series really are just identified as a sequence of partial sums.